In this video, we're going to be working on exponential growth and decay models. So we're really going to focus on just some word problems involving exponential growth and decay. So let's first of all talk about the general format of these types of problems. When you have quantities that are increasing or decreasing exponentially, then you can model them using either the equation y equals a times 1 plus r to the t, or sometimes you'll see it as y equals a times b to the t. If that's for exponential growth, and if it's a decay problem, the only thing that changes is it's 1 minus r to the t. So these are exponential decay problems. The A is the initial amount or the initial quantity that you're going to start with. Your B, or your 1 plus r, is your growth or decay factor. If you have it in the form of 1 plus r, then we call r your rate of increase. And then t is your time, depending on what quantities you're going to be working with. Time could be years, days, hours. So those could vary as far as the units. So let's look at a problem. A city's population was 2000 was 7,500, and it was increasing at 1.6% per year. What will the population be in 2010? So let's first of all come up with an equation. Since I know that it's increasing, it's an exponential growth problem. So it's a 1 plus r to the t. A is our initial population. So in 2000, initially we had 7,500 people. R is my percent increase, which is 1.6%, but that would be 0.016, and then to the t. Now, remember that we could go ahead and combine that and make that 1.016 if we want to, and that's our growth factor. So sometimes you'll see a problem that will ask you, what's your growth factor? So in this case, it would be 1.016. So then if I look at the equation, and we'll go ahead in this case and add those two together. I want to know what will the population be in 2010. Well, 2010 is a time, so that's a t. Now, one of the things that you have to be very careful about with these problems is to see when did you start measuring this. And notice that the initial year was 2000. So 2010, I want to let t equal 10. So then I'm going to grab a calculator. And put that in. So I would take 7,500 times 1.016 to the 10th, and I get 8,790.19. Since these are people, we're going to want to round to the nearest whole number. So our population would be 8,790 in 2010. So let's move on to another problem. This time we've got a culture of bacteria. It begins with 1,000 bacteria, and it's increasing 23% per hour. So A says that we are to write a mathematical model. Since we are increasing, we want to use A 1 plus r to the t. So in this case, we had 1,000 bacteria to start with. 1 plus my rate of increase would be 23%, which would be 0.23 to the t. So we could write our equation as 1,000, 1.23 to the t. Then the question is, how many bacteria will there be in one day? Now you do need to go back and look, because the units here were hours, so I need to convert one day to 24 hours. So then my equation would become 1,000, 1.23 to the 24. So again, we can grab a calculator. We want 1,000 times 1.23 to the 24th. and I get 143,788. That's the number of bacteria that I should have at the end of one day. So that was 143,788 bacteria. And the next question is, when will there be 25,000 or 250,000 bacteria? Well, in this case, this is my y, and I'm trying to solve for t. So then my equation looks like this. When does 250,000 equal 1,000 times 1.23 to the t? Now remember that to solve these equations, we use our graphing calculator. And I normally put that in y1 since it has my variable, and that in y2. So let's go through the steps with the calculator. So go to y equals. In y1, I'm going to put 1,000, 1.23 to the x. I don't want to change the variable, we'll just leave it as x. And then in y2, I'm going to put the number that I'm looking for, which is 250,000. Now, this is always the part that we have the most trouble with, and that's setting up our viewing window. So if I go to window, remember that x, which in our original problem was time, that stands for time. Well, we know that in one day we had 143,000, so that was 24 hours. So we're going to need to go out several hours to get out to 250,000. So let's try x min to be 0, and we'll try our x max at 50, and we're going to count my tens. Now my y is actually much easier to do. I want to know when I hit 250,000. So then I pick a number less than that, and I'm going to go 200,000. And then I'll pick a number bigger than that, and we'll go 300,000. And I'll count by, let's say, 50,000. Right? And we're going to graph. Now what I should see is hopefully an exponential graph, and then we're going to see a linear, a horizontal line where they're going to meet each other. What I want to know is where is this point right here where they're intersecting. So to find that, you go second and trace, and go down to number 5, intersect. First curve, we just push enter. Second curve, we just push enter. And then we can just move our cursor over using our arrow key and get close to where they meet and push enter. And I get 26.67. So that's my time. That's how many years it's going to take me to get to 250,000. So T is 26.67. So normally though, if they give me a beginning time, which in this case they don't give me a beginning year, I would, if they gave me a beginning year, I would add that to whatever year you started counting or whatever year you first made your measurement. One more problem. We have a car that was purchased in 2005 for $15,000. It depreciates 11% per year. So let's write a mathematical model. So because it's depreciating, that's the same thing as decreasing. I would have y equals a 1 minus r to the t. So a is my initial amount. I originally bought the car for $15,000. My rate is 11%. So if I want to, I could go ahead and simplify that, which would be 0.89 to the t. Now, I want to know what would the value of the car be in 2009. So I want to look at 2009 as a year, so this is time, but we started in 2005. So let's let t be 4. So then I would have 15,000, 0.89 to the 4th. So put that into our calculator. $15,000, 0.89 to the 4th. And we get that our car has a value now of $9,411, and we'll round that to 34 cents. So $9,411. $411.34. Then the last question, during what year will the value of the car be 5,000? So now I know the Y value is 5,000, so I want to say, when would 5,000 equal 15,000? 1 minus 0.89 to the t. So we're going to do, that's Y2, that's Y1. So using my calculator, go into Y equals, I'm going to have 15,000, 0.89 to the x. And then I want to know when this was going to equal 5,000. So set up my window. So x is time. Think about what would be a reasonable time to keep a car. So maybe we'll look at the car out to 10, 15 years. Let's go out 15 years. And the x scale, we'll count my ones. My y was 5,000. That's the number I'm looking for, so we'll go below that. So let's go to 4,000. And then my y max will be 6,000. Whoops, too many zeros. Let's take one off. And we'll count my thousands and graph. And so right here's the point that I'm looking for. Where do these meet? So we'll go second and trace. Number 5. First curve, enter. Second curve, enter. Move over close to where they meet. Push enter. And it's 9.4 years is my time. So t is 9.4. But remember, this said during what year would we expect the value to be 5,000? Well, when did we start measuring? So if we go back, it started in 2005. So if I take 2005 and add 9.4, I'm going to get 2014. So somewhere close to the middle of 2014, I would expect the value of the car to be $5,000.